Tell us more about why the automotive industry needs Rust.
Excellent. So this is my topic for the day. I've given versions of this talk a few times. There will be some code in this talk, and I was thinking about like de-teching it a little bit. Then I was like, I'm going to Silicon Valley. This is the place where I can put code on the screen. I can't pull this stuff in Detroit. So a little bit about me. So I spent about a decade in automotive. I was doing a lot of controls and calibration, kind of worked across the established big OEMs, some startup OEMs, as we heard. Very much just, I was a car guy. I loved cars. I just wanted to do something with cars. So I got into the industry, studied mechanical engineering. As I worked, I was writing more and more code. I was working with the controls engineers, and I was starting to get the sense that maybe this whole software thing is going to stick. And maybe the car is the software. Also, while I was doing my calibration, I was realizing that software tools are this absolute productivity multiplier. I was processing my data using software and stuff like that. So that was kind of my realization moment where I thought, okay, the automotive industry, we need better and more innovative tools. So I kind of transitioned into, I was learning Rust. I was attempting to kind of apply some very tech industry software development practices. I was listening in on this whole SDV conversation, trying to figure out what they meant by all that, exploring this whole ecosystem of new engineering startup tools, getting really, really engaged in this. And then I kind of finally made the transition to working in tech. So all this to say, I actually started off as just like a general tech and Rust enthusiast, and then I got a job because of that. So I'm here on the dollar of my company, but I'm just here because I just want to talk about this stuff. So now I work for a company called Pictoris, and I will shout them out a little bit. The aforementioned dollar of my company, I have to give them a little bit of credit. So we're basically building a model-based development tool. So it's a Simulink alternative. So this is a software for designing complicated control algorithms and diagrams. Then we generate memory-safe Rust code. So if you want to talk more about controls development, if you're a Simulink user, feel free to reach out to me and we can chat about that. But we're going to get into Rust. That's what I'm here to talk about. So why does Rust exist? What is this programming language? So first off, what is Rust? I think this is a pretty software-oriented group. So basically, we're talking about a compiled, statically typed programming language. It operates without a runtime or a garbage collector, and it compiles down to bare metal. So at a very high level, if you know a little bit about programming, that should give you some idea. We're talking about something in the C, C++ kind of world. Real low-level stuff. Historically, we would call Rust a systems programming language. I think the Rust Vision doc says it's a software for building foundational software. So that kind of gives you a scope of, I'm going to dive in here, and I want you to know what we're talking about. So Rust has this promise of correctness. And this is a diagram from a talk that was given, I think, 11 or 12 years ago, early on in Rust development. And it was this idea of, you have these low-level languages that give you a lot of control, and you have these high-level languages that give you a lot of safety. Why can't we put a language up there? Why did we just decide that you have to be on this line? So that was the entire idea of the language, and they started to develop it for safety and reliability. So we get a couple things out of Rust. We get memory safety. So you have this memory ownership model we're going to talk about that gives you no memory leaks, none of these terrible memory bugs. You get this really expressive type system that makes it easy to write correct software that enforces correctness while you run it and while you compile it. And you get all the modern tooling. So you're not dealing with disjointed build management tools. Let's have everything integrated and ergonomic, and let's take all the best lessons of software from the last 20 years and put it into one language. So that was what they set out to build when they started to build Rust. There's this whole idea of if it compiles, then it will run. So the idea is that the Rust compiler throws an error when a program could fail at runtime. When there is some piece of data that you can maybe pass into this function that would cause an issue, the compiler would say, I'm not even going to compile that. You don't even get to put that code into production and find that bug later. And what that does is it shortens this feedback loop. So kind of these legacy languages, you get this slow feedback where you design your software, you write the code, you compile it, you get it out in the world, or you get it out into testing and you run it. Then maybe you find a bug, and then you repeat the feedback loop. Rust was trying to do this fast feedback loop of how do we, every time you hit compile, tell you how good your software is going to be. So memory safety, I have to talk about this a little bit. Who has heard the term memory safety before you heard about Rust? Okay, so like you're pretty aware of, memory safety bugs have really become the boogeyman of the closet of the software industry. All of these other massive software companies are starting to realize that unsafe bugs have been the problem the whole time. And you kind of see this 70% number pop up from all of these different independent studies. So the Chrome and Android team did a survey of their, I think CVEs maybe, and came up with 70%. Microsoft found the same number. Project Zero is, I believe, a Google project, but is basically cataloging in the wild 0-day exploits, and they found right around there. So pretty much everyone's realized that memory unsafety is a big problem. Other people who have realized this are Microsoft, who Mark Russinovich basically tweeted randomly one day that he thinks that they should get rid of memory unsafe languages because they were causing so many problems. And Microsoft effectively has and is rebuilding large parts of their infrastructure in Rust. But also the National Security Agency has, over the last 4 or 5 years, been increasingly pushing harder on all of their suppliers to stop giving them memory unsafe code. And there's kind of this transition away from C and C++ and towards memory safe languages. So memory safety became a big problem, and now everyone's looking for a solution to this. So you can find Rust pretty much everywhere. You can find it all over the Linux kernel and the applications that ship with Linux. You can find it in the Microsoft Windows kernel, Google Chrome and Android. Every single hyperscaler is writing not just their cloud software, but their hardware embedded software in Rust. Domestic robots are written in Rust. There's also Rust code running in space. I can't tell you whose, but there's a couple different people who sent Rust to space. So all this to say, even though Rust is sometimes looked at as a bit of a new language in the tech scene, you actually can't get internet on your phone without those packets going through Rust somewhere along the way. It's actually very widely deployed. But what it is not in is automotive. So why do we need Rust in automotive? Automotive is techifying in many, many different ways. If you've come to any of these other events, you've probably heard about one of the ways in which automotive needs to be more techy or is getting techier. Cybersecurity is a huge issue. We have these upcoming cybersecurity regs, largely out of Europe, but even some out of ISO and SAE as well. Porsche sunsetted a couple of models a few model years early because they wouldn't meet upcoming cybersecurity regulations, and they had to redo the entire software stack to get there. You also have all these connected features. So all these SDV initiatives are making every part of the car connected. You have these zonal architectures that are redrawing the system boundaries, not based on the hardware that's connected, but how you want to orchestrate your software. And then you also have industry crossover. You have more and more crossover between automotive and the software and tech industries. You want common tools, you want common technologies, you want common best practices. The legacy automakers want to be able to hire the best software people and not reteach them everything about how to write software. So those are kind of the trends that we're looking at. New tech brings new talent. So this is a very often cited survey for, I think, the last 8 or 9 years running. Rust is the most loved language on the Stack Overflow user survey. It just regularly dominates. People love writing Rust. Automotive needs to be a prestige employment industry. If we want the best talent, we need to be the kind of industry that talented engineers want to work in. The best engineers want to work with the best technology and tools. And people are your biggest differentiator. So if you need to pick a tool because it's going to get you better engineers, that's probably an investment worth making. Just anecdotally, when I'm at broad tech conferences and I tell people that I work in the safety critical embedded space, usually you expect them to make an excuse to go check on their friend across the room. And especially in the Rust world, you get people saying, oh, wow, that sounds really interesting. Tell me more about safety critical embedded software. And I'm just like, it was not like that 10 years ago. This was not a cool place to be in tech. But I think you introduce some interesting new technologies and new languages, and all of a sudden people are really keen on what's going on in this space. So the automotive industry kind of has these two very disparate worlds. You have low-level, deeply embedded C and C++ and Simulink and RTOSes. Then way over here, you have connected features and HMI, and you have embedded Linux and cloud and DevOps and CI/CD. And especially at any established automaker, like these two islands don't talk to each other. They don't know where the other one sits in the building. They don't know what their names are. Like there's no crossover. And basically, Rust is the language that can build a bridge between these two islands of software development. And I think that's really, really important, especially as we try to make cars more holistic. An example I always use, because I know we have a lot of Rivian people here, is last Halloween, Rivian did their Halloween costume software update. And they turned all the R1s into kit, and they had like the front LED light bar do like the red light, back and forth. And journalists loves it, and users loved it, and everyone loved it. And you go to like a legacy automaker and you say, what would it cost for you to do that feature? And they're just like, not for all the money in the world. Like we'd have to write a new contract with that supplier, and there'd be a 6-month lead time in the software, and we can't even push software to that, module. So I think that's just a good example, an anecdote of why we need to make the whole car much more homogeneous in terms of we need connected features down in every single ECU to enable every single feature. So how does Rust actually work? And this is where I try to give this presentation at a high level, and I'm talking to management who doesn't really want to go techie, and it just sounds like I'm making all these wild promises, and it's some AI-powered thing that it's like not real. So I always want to find a way to get down into the language, at least a little bit, to say like, no, this is actually possible. We can actually write better software. And luckily, I think this is a crowd that I can go pretty deep in detail. So memory safety is the first one. So how do we solve the memory problem? So there's a couple of different options. You can use what we call stop the world garbage collectors. So Python, for example, is a garbage collected language. Every X number of milliseconds, the Python runtime just stops all of your execution and cleans up your memory. Or you can have very semi-manual memory management, like in C and C++, where you have to manually allocate and deallocate memory when you're done with it. And that is really risky, because if a junior software engineer forgets to deallocate a piece of memory, there you go, you have a memory leak, or you have a use out of bounds error. So you can either basically have slow and safe code, or you can have fast and very dangerous code that with a lot of what we call our foot guns. We say the C has a lot of foot guns in it, a lot of good places to shoot yourself in the foot. So the way Rust tries to solve this is every piece of data is owned by a part of the program. And as you move your data around the program, it is transferring ownership. It uses lifetimes to basically figure out how long each piece of data should last, and when it can be dropped. And then you also have these smart pointers and a borrow checker to figure out that you don't have any dangling pointers, or what they're called. So these are kind of some of the features. We have the borrow checker and we have lifetimes. And the common types of bugs they solve is the borrow checker kind of solves for the dangling pointers and out of bounds access. Lifetimes solve for like use after free and memory leaks. And so what that looks like in actual code is when I hit compile on this program, the compiler will figure out, OK, we created text here, and then we created a new scope, and we created another piece of data here called user, and then we're going to use user, and then user is actually dropped from memory because we leave this scope. And the compiler knows we don't need that anymore. I can just basically add the drop command right there for you, and then we use our piece of text data, and then that's dropped as well. So you could write this in a more manual language where you're actually allocating and deallocating at every step. But the compiler, the Rust compiler, just knows when you are and aren't using the information. So it just puts that in for you. And it never gets it wrong. We also have what's called the borrow checker. So one of the big problems with legacy languages is when you use pointers and references to things. If you create a reference to something and then the initial piece of data is now no longer in use or gets deleted, that reference might be referring to just some random address in memory. And maybe that means that your compiler will have a bug, or maybe the thing in memory is now someone's password or some sensitive data. So a lot of these cybersecurity vulnerabilities you hear about is because someone was able to use like a dangling reference to get access to data that the program was not supposed to have access to. So Rust handles this with what's called the borrow checker. And there's 2 rules to the borrow checker. Rule 1 is any borrow has to last for a scope no greater than that of the owner. So basically what that means is that I create my data here, and then, I create a reference here, and then I create a piece of data. I put a reference that piece of data here, and then it will actually error, because it says, you created a reference in this scope, and now you're trying to use it out of that scope, and this piece of data is gone. So this is a situation that might be a dangling pointer. but the compiler won't even let this code compile. You can't even put that cybersecurity vulnerability out into the open. And like I said, that's 70% of all cybersecurity vulnerabilities. So like you just saved yourself a lot of headache. Rule 2 is that you can only have either many immutable references to a piece of data, or you can have a single mutable reference to a piece of data. And this is important because you don't want to create a piece of data and have a bunch of things that are referring to it, and they're expecting to get, the current username of the logged in user or some other piece of data, and then you have another reference that goes and changes that, and now all those other references that were expecting something static and constant and reliable now are going to fail. So this code works because I'm going to create my string up here, and I'm going to have 2 immutable references at one time, and that's fine, and I use them, and then they're dropped and they're gone, and then I'm going to create a mutable reference that now is something that I can change and I can work with, and this code works, but if you change the order of this, the compiler shuts it down. So that's, again, a very high level. This is something that if you read the Rust book, you're going to spend a couple of chapters on understanding this and understanding how to write this code. But when I say that Rust magically solves memory-safe issues, I don't want to gloss over that too badly, because this is something that is possible now. A little bit more ergonomic is the type system. So Rust has this amazing expressive type system that allows you to represent your data really well. We call it an algebraic type system. So one of the basic structures is just called a struct. And this is just a piece, this is just a class that holds some data. And you can add methods to your struct. So here I've created a struct for time, so hours, minutes, seconds, the time zone, and maybe whether it's PM or AM. And then I created something that returns a string of that time. Very simple. One of the weird things, though, is that structs can't do any inheritance. So inheritance is something that's very common in language, where you might have kind of like a generic animal class, and then you have like a dog class and a cat class and a snake class that all inherit properties of animals. And Rust doesn't let you do this. This won't compile, which is a little bit weird because that's very common. This is object-oriented programming. Everyone loved it. Everyone used it. Like, why is this a bad idea? So my example of this is always that you kind of have this hierarchical inheritance structure. So I say, OK, we want all the animals. And these are canines and felines and bovines. And that gets you dogs, wolves, lions, house cats, cows, and bisons. Like, this looks pretty reasonable, right? That's like about how people would sort that. But then, OK, well, what if the thing I care about is animals that you can pet and animals that you cannot pet? OK, well, now I'm looking at a different structure. So maybe I rearrange all my classes. Now I have petable things and things that you probably should not pet. OK, so this makes a little bit more sense. But now I care about things that you can eat. And now we have yet another structure, which doesn't match the one, and you're going to have a different inheritance structure. And a lot of the times when you refactor massive parts of your code bases, it's very often how you decided to arrange these pieces of data. Like, this is usually what drives a lot of refactors, at least for me. This is starting to become problematic. So what Rust uses is something called the trait system, which is where we don't care about what a thing is. We actually just care about what you can do with it, which is really like programs are agency, right? They're doing things. This is the more important way to organize your data. So I can define a couple of different traits. I can say that anything that has this trait is edible. Anything that has this trait can be pet. And they have different functions that can be called within that trait. And I can make a struct for a cat. And I can say, OK, implement pet for cat. And I can write whatever function defines how you'd pet a cat. And then, this is the important part, I can write a function that says, give me anything that you can eat, or give me anything that you can pet. And that way, you can use this version of polymorphism where you can write your whole data structure and not have to rework it every time you change what you want to do with your data, and not have to refactor. You can just use this trait system to only care about the thing that you actually care about, which is what you do with your data. This is kind of referred to as make invalid states unrepresentable. That's a really common phrase within the Rust world. So if there's an invalid state for your program or your data, like, your program shouldn't even be able to get there. You shouldn't even be able to get your program into that broken state. So traditional languages and like Simulink, they offer this really expressive happy path. So you can easily write what your program should do. And now you want to go in and start to talk about, well, what are some other things that it shouldn't be able to do? And a lot of these legacy languages, that's where they fall apart. Like, that's where you're going to have to start to write all this complicated spaghetti code, and it becomes really difficult. So you start your system, And what you want to get to here is valid system execution. But what you really actually have to care about is all of this other stuff. You have to care about, did it initialize correctly? Do you have a faulty peripheral? Do you have invalid data coming out of memory? Do you have signals that are missing? And this is like what gets you, especially in a complicated system like a car, where you have this very distributed system with all these ECUs. And so really, like, if you can write the happy path, great. That's kind of the easy part. That's table stakes. It's how easily can you handle everything else. And this is something that Rust has spent some time thinking about. So we have these things called enums, like enumerations. So an enumeration just is a bunch of different things that it can be. So this one is an enumeration for a sensor, and that sensor can be off, it can be on and have a value, and maybe it can be faulted and have like a fault code of some kind. So that easily allows you to define the state of your system. So everything can have an enum that defines its state, and then your enums can also contain your data payloads. But where this gets really useful is now you can use like the match statement. So if you have some piece of code that wants to refer to this sensor, you can actually match on, well, if the sensor's off, maybe I should return a default value. And if the sensor's on, then I should certainly return the value the sensor is reading. And if the sensor is faulted, then maybe I just want my code to panic because that's a problem and I can't run this algorithm. So having that type of like, how do you handle these unhappy paths built right into your language means that as you write your code, you're just naturally handling all of these weird little fault conditions. You're not going back through. And one of the nice things about this is it actually requires you to match every single case of an enum. So some of the enums that kind of have emerged in the Rust language and are now used everywhere are the option enum and the result enum. And so the option enum is there is either nothing there or there's something there. And the result enum is something either went OK, and here's the thing that you got, or it errored, and here's the error that happened. And almost every signal in like a vehicle or a piece of software is actually one of these things. It's almost never just the data, because a lot of your data is going to come from another sensor, another ECU, or from the internet, and like it might fail. So realistically, like this is kind of how we should be thinking about our whole system. And like I said, there's something called forced pattern matching, which is where if I have an enum with off, on, and faulted, and then I want to write some software that uses that state of the sensor, it'll actually throw a compile time error. It will say you didn't cover like what if that sensor is faulted. And again, that's really valuable. If you're writing something like a battery SoC monitor that needs to calculate exactly what the state of charge of your battery is, and you're relying on all these different sensors, like if one of those sensors is faulted, like what are you going to kick out for your SoC? Is there a chance that it's going to get railed to infinity or something? Like you need to handle this in some of these critical algorithms. And having a language that forces you to every single time just means that you write better software. This is like one of those things that like activated me on Rust because I was debugging these problems on vehicles, thinking like there must be a better way. So kind of to think about this type system and something that could control algorithm, if you have a sensor that gets read, maybe that just comes in as a pure numeric value because it's always pretty reliable. But if you have something that comes in off of a CAN device driver, maybe that's an option because it can either be there or it can not be there. And so now you have to handle it not being there in other places in your algorithm. If you have a memory read, maybe that's something that can fail. Maybe that memory can be faulted. So maybe you need to handle the fact that it might fail. So as you kind of structure your system and your algorithm, you actually really want to think about what actually is all this data? How reliable is it? And do I need to handle all of these like paper cuts of faults throughout the system? One of the things that Rust has is modern tooling, like I mentioned. So we have Cargo and we have Crates.io. So Cargo is this all-in-one package and dependency manager. If you've used like Anaconda in the Python world, it's a little bit like that. It pulls all of the dependencies. It manages your tooling. It creates your virtual environments. It also has built-in automated unit testing. So you can write unit tests alongside your software, and that's all built in. It's like the easy thing to write. You can generate docs from your code comments. It also has a lot of interesting extensions that we'll talk about. And then we have Crates.io, which is the library repository. So again, similar to something like PyPy, PyP, or what's the NPM, the Java one that had the left pad incident. Yeah, we love those guys. And these are just kind of table stakes for like a modern language. They're really, really useful to have. But like some of those cargo tools get really interesting for like an automotive context. So you have cargo tools like cargo deny that will check the licenses for all of your dependencies to make sure that someone didn't accidentally pull in a license that you're not allowed to sell software on. Or you can audit for unsafe lines of code or security vulnerabilities, or you can just clean up your dependency tree and get rid of code that you don't want. And this, like I said, starts to become really, really interesting, especially for the safety critical use case, where you could actually maybe like cargo audit for whether or not all of your software is like ISO 26262 certified. There's also a ridiculous number of formal verification and testing tools for the Rust world. This is another one of those things that you go into any other programming world, and this is weird esoteric research stuff that like your comp sci professor cares about and is too slow to like use in production. And yet in the Rust world, everyone loves the idea of formal verification because the community is so obsessed with correctness. So there's all of these different formal verification libraries. There's automated testing. So Cargo Fuzz is a fuzz tester. Prop Test is property-based testing. You have some traceability libraries, so actually tracing a requirement from your requirement generation through your source code, making sure that everything was tested. So it's a really, really lively ecosystem for that in a way that still, frankly, catches me by surprise. So is it certifiable? That's a question that we get a lot in this safety critical world. Rust has been put into production in the IEC 61508. So Sonair, a Norwegian company, actually certified at 61508. And all of the tooling is present for 26262. So we have 3 different certified compilers. We have some static analysis software. CoreLib has been certified. StandardLib hasn't yet, but that's just a matter of time and money. And then we have requirements tracing, which is part of the 26262 story. So I'm involved with the Safety Critical Consortium, which is part of the Rust Foundation. And this is basically the question that we've been trying to answer. We've been trying to identify the gaps in the certifiability story, make sure that vendors or open source projects are filling those gaps. And we're pretty much at a place where if an OEM wanted to go to 26262, they absolutely could. MISRA Rust is interesting. So if you work in the embedded C world, you've probably heard of MISRA C. It is the rules of all of the things you shouldn't do in C because there's a lot of foot guns in that language, like I mentioned. And so we get this question of, well, is there MISRA Rust? And so the team over at MISRA went through the 223 MISRA C rules, and they identified that almost 70% of them basically just don't even apply to Rust. Like in the document, it's like, well, the compiler handles that, the compiler handles that, the compiler handles that. So technically, yes, MISRA Rust is coming. And if your organization is concerned about MISRA code compliance, we can get there, but it's kind of irrelevant. Like MISRA was invented to solve all the problems with C, so was Rust. And an interesting anecdote here is we're working with the Rust team, the compiler team, and like the tooling team to basically put the MISRA code guidelines directly into the compiler and the tooling. So you can actually just like run a Clippy lint, which is like the code linting, and make sure that all of your code is MISRA compliant. So instead of spending thousands of dollars for like a static code analyzer tool from some esoteric company that you've never heard of, it's just built into the language, and it makes it super easy to make sure that all of your code is certifiable. So like, what does Rust unlock for us? Security, especially future-proofing against cybersecurity regulations. This is going to be really important in the automotive space. There's a lot of people talking in the SDV world about let's make everything on the car internet connected. There's a lot of people talking about cybersecurity, of maybe internet connected things are a little bit dangerous. They're not always in the same room, so we are going to have to kind of figure out how these deeply connected cars are also going to be cyber secure, and that means security throughout the entire system. Velocity is a big one. So because of all of that modern tooling and because you get so much feedback from the Rust compiler, teams that switch from C and C++ usually report that after about 4 to 6 weeks, they're developing way faster. Unity is really important. I think focusing on one language and technology that can run everywhere from the UI to the embedded control. We were talking before I started chatting about, does this apply to the SDV space? And this absolutely can, right? I think some of the OEMs, this is kind of where they started Rust in their infotainment and their SDV world. They were doing more, of that high level, and then this kind of cascading down into the embedded control. And it's really valuable to only have to focus on one language for that org. Safety, fix your code as you compile, not when you run it, not out in the vehicle is really important. Speed is really, this isn't one I talked about a ton because we're really talking about like the embedded context, but because Rust is a compiled language, it's like 168 times faster than Python. So especially if you're looking at other high-level, more expressive languages, you're going to be burning a lot of CPU cycles, on kind of those more abstracted languages. And then the toolkit, I think, is just such a joy. So nice to work with. Volvo is a company that has been extremely prolific in the Rust space and also really happy to share their experiences. So they implemented a full ECU in Rust, and the results were pretty fantastic. So they said that they averaged out to half a bug per developer per year on the team that worked in Rust, which they said was about 100 times better than their legacy projects working in C and C++. Julius, who I pulled this slide from, he gave a full talk at Rust Week a couple months ago. You can take a look at that, but he's pretty glowing about how well it worked. So they're kind of like our terrific user story. So where are we at with Rust adoption? So there are automotive OEMs who are working in and around Rust. So all of these OEMs either I know are doing Rust, they're open about doing Rust, or they're at least like hiring. Some of these OEMs, Rust is showing up in all their job postings, which gives you a pretty good feeling for how they're using it. Woven by Toyota is particularly very bullish on Rust. The hardware story is terrific. So Espressif, who makes ESP32s, has awesome support for Rust. But even Infineon, who makes the tri-core ISO 26262 certified MCUs that are in most automotive products, are very enthusiastic about Rust. Pretty much every big software supplier is doing something in Rust. So Bosch, Electrobit, Vector, ETOS, and Aptiv are kind of like the usual suspects, especially in European automotive, and they all are pretty heavily involved in the Rust community and doing Rust projects. And then we also have some really cool startups. So OxidOS is doing a fully certified RTOS to run in Rust. Vehicle has some kind of runtime SDV type stuff. Ferris Systems, they make one of the certified compilers and they've released white papers on MCDC and Rust, and they have a bunch of really interesting projects. And then us and Pictoris are kind of bringing that MBD story into the Rust ecosystem. So we're well on the way in terms of adoption and suppliers. So
sorry for interrupting, but you assume more are coming, I guess.
Yeah, there's definitely.
What are concerns? I'm not sure if you're going to get there. What are concerns from those, let's say, OEMs that are not listed there? Are they just laggards, or do they say,
There's a little bit of that. I've had chats with OEMs who, what I think that the big concern is the switching cost. I think that it really comes down to, even if they don't really have an argument around, yes, we know this is probably going to be better, we're excited about it, but they have so much deployed infrastructure in C and C++. And what I found is like certain industries are very happy to switch. Space industry being a great example, that they pretty much work on one product at once. They jettison it into space and never think about it again and then start on the next one. On automotive, we don't really get to do that. The larger companies usually have multiple different platforms with multiple products on each platform, all running in parallel, all running on the same processes. There's just no good breaking point to switch their tooling and languages.
Along those lines, what about the foreign function interface? I mean, if you wanted to transition your code base to Rust and start writing new libraries in Rust, obviously that would be a concern. And in particular, for applications, you have a libc, presumably, that implements the system calls. You have to deal with any comments about safety in that environment?
Yeah, so FFI is, that's what she referred to a foreign function interface, which is commonly referred to as FFI. So from the get-go, Rust was designed to be able to interop with C code because the developers of Rust knew that it was going into that world. So it's really easy to call Rust from C and C from Rust. So most of the companies that switch are, they're not eating the whole elephant in one go. They'll usually pick some element of their system and rewrite that in Rust and then use the FFI to interop with their existing C and C++ code. You reference the safety of that. That becomes a little challenging because in some ways it erodes the safety promise of Rust because now you have a bunch of C code in your library and you have this interaction. And it's less so that the FFI introduces bugs on its own and more just that you have a bunch of C code, which is a valid concern. There's also something called unsafe rust. So if you, for some reason, especially with microcontrollers, you sometimes need to just do direct memory access and you can't have the borrow checker getting in your way. So you can create these unsafe blocks, which pretty much allow you to be more unsafe than like default Rust. So one of the arguments against is like, well, I can switch to Rust, but I'm still gonna have a lot of C code. I'm gonna have a lot of unsafe Rust blocks. Like, what's the point? It's a valid concern, but also it's a little defeatist, right? Like if you're saying the C code is so unsafe that like having C code in your system like negates the value of Rust, then that feels like a good argument just to, you know, move forward in some way. So I think there are some valid safety concerns with having the two systems interopt. There's also a cost concern with, okay, now we have to maintain 2 tool chains and 2 skill sets with our developer team. But I think that if you see the benefits of Rust enough to see the downsides of having the FFI, then you probably see the benefits enough to like push through anyway. You know what I mean? Okay, we're just in the Q&A section at this point. So I had one more slide about, you know, if you want to learn Rust, you know, there's like a book that will allow you to walk through the entire language, you know, have various examples, and that'll get you pretty well up to speed. The Rust Safety Critical Consortium is an organization I'm involved with that was founded about a year ago by the Rust Foundation, and we're a consortium of companies who use Rust, so your automotive OEMs, your aerospaces, as well as kind of these tooling providers like some of the ones on the previous slide, as well as some folks from the Rust Foundation and the Rust team trying to identify where are the gaps in the ecosystem, where's the communication gaps, where's the tooling gaps, where's the standards and coding guidelines gaps, and fill them. So if you're interested, you can get involved there. This is my company, Pictoris, doing MBD with Rust, and you can also just reach out directly to me via email or LinkedIn.
Okay, thanks a lot, Simon.
Cool.
Fly through. I don't claim that I understood everything, but there's time for questions.
Yeah.
If you deliver software to an OEM, to Rust software, what kind of requirements do you see? Do you see Mizra Rust as a must-have?
So I think one of the problems is that the way software is delivered to OEMs, you know, especially the legacy OEMs, is very much, well, I just want to buy a box with a CAN DBC and I don't really care what's on it. So the software interop between the OEM and the supplier, I think, is maybe one of the problems that we're trying to solve with SDVs, so that you can actually buy like a container or something like that. But that's one of the reasons why tier ones, you'd actually notice that you didn't really see any tier ones in that list. And that's because they really have to be fast followers with the OEMs. They pretty much have to deliver what the OEMs would expect and what they would develop. And they're not really in a position to go blaze a new path in software tooling because their customers, the OEMs, expect to have something that follows pretty well-known standards. So, you know, right now, I think that's kind of a, you know, that's why so many of the OEMs are leading. And, you know, to your point about like, would you see Mizra Rust? Yeah, you'd probably see Mizra Rust. I think a lot of people in the Rust world want to kill Mizra Rust because the whole point of like why they wrote Rust is so it wouldn't need a Mizra. So it's a little bit controversial within like the Rust and the safety critical world, where a lot of people are like, no, we're trying to move away from that. Like that wasn't supposed to follow us from C-land.
Compare and contrast Pictoris MBD with AutoSAR.
Different products. So Pictoris is like model-based development is a drag and drop like block-based controls diagram that generates code. So you can generate either out of Simulink or Pictoris, you can generate like an AutoSAR classic application that you would then run in the AutoSAR framework. So we would have some AutoSAR compatibility, but AutoSAR is more of a runtime. Do you have thoughts on AutoSAR? I know you do.
Do you think Rust adoption is accelerating right now?
Very much. Yeah, I think especially in the last year. I actually was chatting with the team at Sonair, who are doing a really interesting, it's basically a radar sensor that uses sonar instead, and that gives us some interesting examples. And they're the ones who certified their sensor into 61508, which is an industrial standard. So they're selling into mining operations and factories. And they were making the point that, especially in Europe, there is a like safety manager in your organization who's actually personally liable for the safety of the, you know, if there's an accident, you know, they're the ones who, you know, could be held personally liable for it. And the way that you're safe from that is you prove that you are using industry best practices. And if an accident happens in your mine, but you have all the documentation showing that you're using the current state of the art of the industry, you're fine. And he feels that as soon as people realize that memory safety is a thing and Rust is safer, there will be a massive shift in adoption, because no one wants to be on the line if there's an accident and then the auditors say, well, you were using legacy software. Of course this happened. So I think that you're starting to see that kind of fear of regulation driving a lot of this interest. So between that and cybersecurity, I think that's driving a lot of like the massive interest in adoption.
Good for my job prospects.
Yeah, you'll do fine.
I have a question. I guess there's usually a crowd that gets it and it's all in, but then there's usually the other crowd. I guess maybe some thoughts on how we could, or maybe help them or show them the way, I guess.
Yeah. So, what he's referring to is a pretty common thing when you go in and talk about Rust is you meet some, programmer who knows a lot about C and C++ and has basically made their career around the fact that those are really difficult languages to write, but they're so good at software they can write it. And then you show up and say, hey, we made an easier language. And they're like, whoa, 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 that is not what I want. So there is pushback, when you get to people who I think rightly or wrongly, because there's a lot to be said for you have a team that knows how to use this language, you have tooling that works, you have processes that work. I think those are good reasons. But I was actually having a call recently with some pretty senior people at an OEM, so they were pretty experienced. And the call started off with them talking about the switch from whatever language they started with into C. So they're talking about, oh yeah, you remember when we were doing everything assembly or Fortran, and now we all switched into C in the 90s, and they're all just like, all right, like what's the next thing? Like bring it, like we've done this before. So I think there's weirdly, you kind of get to a level of experience where people have seen enough turnovers in the industry, and they're kind of just expecting that there will be change, there will be a new language, and they saw the benefits of the last switch. They'll see they see the benefits of the next one.
Follow up, more of a comment. I know this is a joke. Someone actually told me he will retire before he learns a new language.
I mean, C came out in what, 57 or 61? Like, you've been able to have a career in one language, which is amazing. Yeah. Hey, Jeff.
So my Rust experience so far is not super embedded. It's only like desktop Linux, maybe still embedded, but full Linux environment. So I'm curious if you have any comments on how well suited Rust is in a more like low level, like tiny little weak microcontroller that doesn't have any heat memory in that kind of environment where something like C++ is much more rare because things like smart pointers don't help you out that much, and a lot of the like more advanced language features you just can't use because of the lack of heat. So I'm curious if you have any thoughts on that context.
Yeah, so you do still get a lot of the advantages. So I mentioned these unsafe blocks. So when you do like DMM, direct memory management for accessing your peripherals, you kind of have this like unsafe escape hatch. But then everything else, you do still get the type safety. You still, if you are using any kind of like smart pointers or like dynamic stuff, that becomes challenging. But you do still get, I would say, 80% of like the safety and reliability promises of Rust. There's you can run full no standard. You can run just the core. The core library, which is what you'd run on an embedded controller, is actually pretty full featured compared to some other languages where like you really feel like the train wheels came off when you got to embedded. And then also Rust has a very strong embedded community. So there's some really interesting frameworks. So there's like the OxidOS RTOS guys I mentioned, but there's also something called Embassy, which is an event-driven architecture. It's kind of taking like the async story in Rust and kind of bringing it down to the microcontroller level. And there's a lot of people who are getting on board with Rust on embedded specifically to use Embassy because, essentially it's like this like work sharing kind of async thing where if you have a function that would block because you're waiting for, a peripheral memory read, you have an actual executor that will put that function to sleep and go run some other work. So for something like IoT devices where you're extremely battery constrained and extremely power constrained, there's companies that have switched over to Embassy and Rust specifically because you get the efficiency. So that's less because of Rust being Rust and more just because it's kind of the hot new language in the embedded space. So when people are going to do a really interesting project in Rust or like, in a language for embedded, they do it in Rust. And another thing is ProBAR-S, which is like a debug harness for Rust. It's like a piece of software that allows you to interface with your chip. That integrates in the cargo unit tests. So you can write your software, you can write your unit test directly in your source code, and you can just hit cargo test, and it compiles a bunch of binaries and runs all of your unit tests, not on the computer you're developing on, but directly on your embedded hardware. So you almost get this like baby Hill sitting on your desk. Hill's a hardware and loop tester, like for free. And again, that's not something because, that's not intrinsic to Rust. That's just because someone wanted to write a really cool, feature-focused embedded debugger, and they did it in Rust.
Are there any hardware limitations where this runs on or does not?
Yeah, so not many. I think most people won't find them. So Rust is a really good fit for ARM. There's great support there. RISC-V, PowerPC, x86, x64, all of the common architectures are very supported. In automotive, you get into like Renesas's proprietary RISC adjacent architecture ISA, and like that's not going to have support. So especially you get into like the embedded world and you start to find more oddball microcontrollers where you don't have support. Tri-core was kind of the big one because Tri-core is a very unique microcontroller. So that would have been a big blocker, but they actually invested to have a compiler built for that. So you definitely, there is some limitation, like there needs to be a compiler for your microcontroller, but you're probably not going to hit very many unsupported hardware, in most projects.
And that's also evolving, I guess, that there are new compilers.
Well, and there's a lot of community supported packs. So in the Rust embedded world, we have what's called like a HAL, a hardware abstraction layer. And there's a lot of people who are just pulling the documentation for a microcontroller. They wanted to run Rust on it. They would just write their own HAL. The microcontroller manufacturer had nothing to do with it. So a lot of the common microcontrollers you can run Rust on, the vendor actually had nothing to do with that. But now the vendors are starting to get on board. So Espressif, who makes the ESP32 chips, they're one of the first microcontroller vendors to go all in on first-party Rust support. And the tooling is like awesome. Like they made not just like the pack and the compiler, but they made all of these other cool tools for interfacing with their chips and creating template projects and installing their tool chain. And they are pretty jazzed. They're finding that a lot of people are showing up at the doorstep because they're the people with really good Rust support.
What would you say is the biggest gap in terms of the tools and the maturity of the Rust language at this stage?
I think specifically for safety critical, there's some stuff around like test running that becomes a little bit challenging. So Cargo is like the tooling around Rust. It's like the dependency manager, and it's a very large, complicated internet-connected piece of software. So you're not going to certify that, but that is like the test runner we have. So if you need a certified test runner, you kind of need something else to fill that gap. So you get into maybe like the more esoteric sides of ASIL-D safety critical stuff, and you start to find some weird gaps. But for lower criticality levels, non-safety critical stuff, or non-embedded, you're not going to find a lot of tooling gaps because like the Rust community kind of built the tooling first. That was what they really hyper fixated on while adoption was growing in industry.
Brings up one question, this Rust community and where it came from. Not sure if you said anything about the history when it started and everything. You said C started in the 50s or so.
Yeah, so Rust was started in the late 2000s by a guy named Graydon Hoare, who was working for Mozilla Foundation at the time. And he was frustrated because the elevator in his building was always broken, and it was like a 13-story building. And he knew that it was like dumb C bugs in this like ancient elevator software. And so he started to write a language just to be more reliable.
That's a great story. You should include it.
And the Rust language went through a bunch of very different iterations. Like it was garbage collected for a while. Like the borrow checker was like out, it was like in, then it was out, then it was back in. So they really did try a lot of different stuff to get to something that really met the goal of just being super reliable. And then they did their 1.0 release in 2013. So they've been 1.0 for a while now, but I think during the pandemic, a lot of people learned Rust as their I'm locked in the house project. And then kind of afterwards, 21, 22 is when it really hit commercial viability.
How does formal verification in Rust compare to formal verification in C?
I mean, definitely less tooling out there. So Trust and Soft just released a Rust version of their static code analyzer. There's all of those community projects that I mentioned. A number of these are kind of at varying levels of maturity. They're kind of different. I think Crusoe is kind of like a markup language that you can kind of decorate a function with what it should formally do, and then you can check it afterwards. And Virus is, I think, like a whole other language. And so these are kind of different tools to do different things, but there's a lot of projects moving. I think there's a dream in the Rust safety critical world that eventually certifying Rust will be easier, faster, and cheaper than certifying C. Because we know that we're kind of belt and suspendering this thing right now, right? We know that you're getting all of these intrinsic guarantees from the compiler, and then we're also checking them after the fact, because that's what we're used to doing with C. And right now, to get adoption, we're going to have to do both of them. But the hope is that eventually we can start to look at the auditors and the regulatory bodies and kind of point out, like, hey, we already did this. We don't need to do it again. And you can eventually start to pull some of that after the fact verification out of the process, because once we can really formally prove that the compiler is indeed handling it. And so the hope is that we actually won't need as much formal verification in the language.
Great. Let's thank our speaker, Xander.
Cool. Thank you, everyone.